Okay, let's continue and let's welcome on stage our next group of panelists. Let's talk now about designing versatile infrastructure for cloud, AI, and emerging compute workload. Please join me and welcome as well with a big applause all the speakers here on stage right now. Mark O'Regan, Chief Technology Officer at Dell Technologies, who just spoke with us. Oh, sorry.
I thought you banished me from the room for my...
I was thinking that always a little bit of exercise is good,
Yes.
you know, to keep up the legs moving with all these long days. Let's welcome again as well Peter Hannaford, CEO at EdgeNebula, and Mark Duitemeijer, Managing Director at Global Business Development at VEIR. Moderating this debate, we have Henry Daunert, founder and CEO at OnValue Technology. Welcome to the three of you, because you are already welcome here.
Thank you so much.
Thank you so much, Mark, and sorry about that.
Not at all.
Mark, good speech.
Oh, thanks. Good to see you.
Please.
Hello, Mart. Good to meet you.
Hello, good to see you.
Good to see you again.
Hello again.
Thank you. Okay, so very exciting presentation, Mark.
Oh, thank you.
We are looking for many changes.
I think so.
Okay, so we have three top experts in the data center infrastructure world and computing world. So, welcome today, and we're going to hit, straight into the matter. And we have Mart Duitemeijer from VEIR, okay, and Peter Hannaford, EdgeNebula, pardon me, CEO, and Mark O'Regan, CTO Dell. So let's start with Mark, please. So question number one about all this infrastructure for emerging technologies and so on. Okay, so the world is, in the next 25 years, is going, at least according to forecasts, okay, is going to grow its data center capacity 4.5 times, from 100 gigawatts up to 450 gigawatts in terms of data center capacity. So, first of all, please introduce yourself a couple of minutes, and then you let us know about what is VEIR, how is VEIR going to offer some solution for this challenge, please.
Sounds good. So my name is Mart. I work on commercial development at VEIR. Prior to VEIR, I worked on a bunch of things, design of the European electricity market. I spent some time at MIT looking at new technologies in the energy system, and then joined VEIR. And just to really quickly describe what we do, because we're a startup company, we're a Series B startup company, raised 150 million to date. Some of our investors include Microsoft Climate Innovation Fund, National Grid Partners, and we make superconducting power delivery systems. And that, in a very simple way, means that we make power cables that are 10 times smaller than a regular copper conductor or bus bar. That addresses some of the fundamental, we believe, scalability issues when you move towards megawatt scale racks. And to your question, I think if we think about tripling the capacity, one big piece of that is moving towards those high density racks. And right now we see, and we'll talk about this, but we see a move towards an 800 volts DC ecosystem. But even then, we believe that copper is going to be actually quite prohibitive in those designs, moving towards those type of server racks. On top of that, I think you mentioned the sustainability piece of that. I think if you now think about the amount of power that we need, but also if you think about scope 2 and 3 emissions, so the amount of cement, the amount of copper that we need to put into these data centers, that's a massive piece for sustainability. So for superconductors, how we address those challenges, I'm going to mention one that we don't often think about, but for scope 2 and 3, if you are moving a lot of power around your data center in a massive trench, you have to fill it with concrete, specialized thermal concrete. If we can reduce that size of that trench by 10 or even by 20, we can have a 5 times reduction of sustainability impacts of that cement of the data center. If we reduce copper by 95% in the data center when it comes to power distribution, that's a 5x sustainability benefit when it comes to scope 2 and 3. So there, I would say, moving towards that goal, tripling capacity, that is one of the ways in which we can do some more.
Very good value proposition. Thank you. Okay. And Peter, please.
My name is Peter Hannaford. I've been in this industry for about 100 years, or it seems like it, since before data centers were called data centers. So my company built probably the biggest data center in Paris, the biggest data center in Amsterdam, biggest data center in Prague, one of the biggest data centers in London. And then we sold the company to APC and worked with Schneider. But now my new company, we're now focused on building infrastructure for AI, but using existing resources, using stranded power and redundant real estate to create a network of AI infrastructure, a combination of core and edge to deliver AI where it's needed, which is where the people are.
Oh, very interesting. So you bypass, let's say, the struggles of getting power, and you actually recycle existing locations.
Yeah.
Okay, very smart. Good. Thank you. Okay, and Mark, please, if you could elaborate a little. Well, we already were here, but maybe a short intro about yourself and what is, let's say, Dell's, let's say, strategy moving forward. Although you already gave us an interesting overview.
Yeah, for those who are in the room, that was a very, very quick snapshot, but I hope it was a fairly succinct idea of what it is that we're at. Complementary to both Mart and Peter, what we're interested in doing is looking at data centers, looking at data center consumption, and looking at what I call centers of data, what Peter just talked to there, is where the power needs to be, when it needs to be there consistently, and why it needs to be. And the why it needs to be there is exactly to your point. It's where the AI is, it's where the event is happening, it's where the people are, it's where the things are, it's where the processes are and processes. So there's a ton of different things that range from latency. You know, if you do a round-robin trip just from a pump, an actuator, a camera, a sensor, just to a data center, you're going to incur anywhere between 50 and 300 milliseconds, 350 millisecond round-robin. For AI, that's not good enough.
Yep.
It just will not. The event is over, the thing is gone, the opportunity is lost. If you're in healthcare, maybe even the life is lost. So, latency is a huge thing when you're talking about transmitting information, not just data, but information. And to the guy's point there is how do we actually handle, the transmission of intelligent data and information at the right place and the right time in order to be able to do this. Now, if you come to the edge, so if you put the compute construct close to where the event is happening and then you land the models, so I talked about small language models and maybe even agents that can land down on top of the compute architecture, which are designed to enmesh and then are pulling, as you mentioned, Peter, recycled energy onto that computer architecture. That reduces the latency from, up to 350 milliseconds down to maybe even sub 150 to 200 milliseconds,
Yep.
right? So you're now able to get the experience, the accuracy that you need, and the compute has the energy that it needs to be able to actually facilitate for
So
that.
we continue with
Can I
you.
just say something? I mean, just to finish on the question,
Absolutely, yep.
on the 400 gig number, I mean, yes, it's a big number, and what we're talking about now is compute capacity now. 400 gig, I don't think anyone would argue that it could be 400 gig, but how does that get delivered? When you think that 75% of that is going to be in inference, is the prediction, is inference best delivered from a hyperscale data center that's 5,000 miles away? It just doesn't make sense. So
It can't
we
happen,
need to think about how we're going to deliver this compute capacity. Don't forget the power demand that extends over the whole landscape. But where are you going to deliver this? I mean, and stuff's getting smaller and smaller now. I mean, NVIDIA bringing out the VEIR Rubin, which is 250 kilowatts in a rack. You could get a 2 megawatt data center on this stage. That's what we're talking about. We don't need big hyperscale data centers.
Brilliant point, Peter. And just so we all understand exactly what that means, if you look at large language models, small language models, agentic functions, smaller and smaller. If you look at Intel and the TikTok process of the last decade, 65 nanometers, 45 nanometers, 33, 22, 14, 8, now we're down to 2 nanometers.
Yep.
Everything is getting smaller. It's not just getting smaller, it's getting more energy efficient. And that's the focus of the industry. And to Mart's point, it's out at the edge, we achieve this by describing what I described, but our relationship at the edge to what's going on in a data center is still fundamental, because the data center has to host AI workloads, of course, maybe some of them that aren't immediate, but also traditional workloads that are just not going away. We're still living with mainframe, we're still living with alpha systems, we're still going to be living with databases and data repositories where we pull real world information around processes and processes continuously. But there definitely has to be a revolution around how we actually handle the compute and where that's going to take us. And I believe it's going to be into, you know, some sort of a symbiosis between AI and quantum.
Don't you think, absolutely, fully agree with both of you, and don't you think that probably workloads, let's say compute workloads, will be more related to application-driven, you know, exactly by the reasons that were mentioned. Let's say if I am, let's say, developing an autonomous vehicle, let's say, application, or I am developing a, you know, a surgery robot, you know, AI, you know, system or solution. This definitely is inference, should be inference-driven, okay? However, if I'm in a, let's say, more probably, you know, ERP, CRM, AI agent built into that application, probably I don't need such ultra level of latency. Do you think the market will kind of position itself, or the application developers will say, hey, for this I can live in a more remote, cheaper location. For this one, I do need to go definitely metro, you know, definitely within a metro area, because I must have a very low latency.
Well, if you need low latency, then you have to be sitting on top of you know, your compute needs to be where the workload is. But there's not that many. How many applications need really, you know, sub 10 millisecond latency? If you're trading, obviously there are applications where it's essential that where there's no human intervention, you need super low latency. But latency is it's a spectrum. Yep. You know, you don't need sub-millisecond, you might need 250. It's a spectrum, it depends where you sit on that spectrum. That's where you're deploying the power to process the workload.
I agree with that, and you know, but of course there will be many applications that we cannot even think of today. You know, for instance, humanoid robots, you know, walking elderly people across the street, you know, traffic lights and things like that. You know, this, you know, it's latency will be irrelevant.
Yeah, it's interesting because we look a lot at this as VEIR because our first application is the high-density AI training data center. So, and if you look at how we see the development over the next, say, 10 years, like right now, there's most compute being built for that, like by far. Like if you look in the U.S., I think it's about 75% of the new loads are going to AI training data centers. But that model flips somewhere around what we see or what we expect, but it's really dependent on also what we develop the models for exactly. But around the 2030s, 2031, we see that flips towards inference, simply because we know that then indeed we need those loads, those data centers closer to the urban centers, etc.
150%. That's completely correct. And both of you are saying is so the way so we talked about this as well, Mart, right? About, you know, this hybridity between these systems. Like I mentioned, so we have mainframes, we have alpha systems, we have things that were built 30, 40, 50 years ago. We have things over here that were built, you know 3, 4, 5 months ago. There's things that are just launching into ecosystems right now as we speak, okay? So you're absolutely right. You can see that from a compute point of view, and I'll get to the applications in a moment, because you're bang on the money, Henry. So when you look at a compute perspective, look at a quantum computer. So I'll pull a quantum computer in front of you here. It's a chandelier. And everybody's talking about it, the chandelier being in its cryogenic state. We talked about this a little bit earlier on. In behind, what most people don't understand is in behind the quantum computer are, you know, systems and subsystems and other support systems that actually drive the quantum computing and help it work. Mm-hmm. There's classical computing in there behind that. Now, there's another thing to understand about quantum computing, and that's this. Quantum computing really works off the rules on the mathematical functions of quantum mechanics, whereas classical computing works on binary, right? Zeros and one. It is or it is not. It's one or the other, 0 or 1. Quantum is somewhere in between, right? So much more variation. So the point I'm making is that if you were trying to relate directly to a quantum computer, that would be like me coming here today and doing the talk that I gave in Gaelic Irish. None of you would understand it. So there needs to be some sort of an interpreter in the middle, and that's where the classical computing comes in. So you've got a classical computing and a computer and a quantum computer, and then as we look at the quantum computers and we look at some of the problems that we're trying to solve, at a, you know, some of, you know, the fundamental world problems that we're trying to solve in terms of hunger, racism, climate change, all of this sort of stuff, that is going to happen in that quantum space. And that's where the energy, to your point, Mart, that's where the energy is going to be directed directly in there. Now, if we continue down the path of classical computing with, Ethernet or even IP networks, it's not going to cut us. We're struggling today. So in 10 years' time, 20 years' time, I'm not sure, I can't remember, was it 2040 you gave me a date or something like this, and what it's going to...
2050.
2050. Yeah. I mean, it's just not going to cut it. It's not going to cut it by the end of this decade, let alone 2050. So I see certainly a world, and relating to the applications, where we're going to have classical, where we're going to have quantum, and then we'll have optical computing in photonics, which uses light to transmit information, and then we're going to put those compute constructs that will be connected in an where they belong. To Peter's point, you're not going to drop a GPU onto a sensor. You're not going to drop one of our compute constructs or one of our data storage architectures out beside a camera. But you are going to push an edge device out there with a level of intelligence across a mesh, and that's where we're going to pull the energy that Peter talked about. One last point on this, and if you look at what's happening in industry, if you look at what's going on with DARPA and the ERP, the Energy Resurgence Program, really interested in this idea of domain silicon on chip. So think about a chip like this with a Google chip engine on it, with a Microsoft chip engine on it, with a Dell chip engine on it. You know what I'm saying? With an FPGA, with a GPU, and you hit the silicon on the chip in order to access the application that you want.
Interesting, yeah.
Very, very interesting.
I saw that at GTC, actually, in a I think, prehistoric form.
And I believe whoever builds that will
with
they're the
PCIe
winners.
slots, but kind of going that direction.
Yes.
Anyway, so just to close this chapter, so Peter, you feel like it's realistic to think that power demand in data centers will multiply times 4.5 in the next 25 years?
We think that AI is going to be a utility. It's going to become a utility like water, gas. It's going to be everywhere. We're going to be using it. So the question is, how does that get delivered? And it's crazy to think that we can deliver it by putting large hyperscale data centers everywhere and not being able to distribute it down to where it's actually needed.
And this is related to everyone. And this is an honest, open question. I mean, it seems to be that to date, inference is kind of a blur architecture. Do you have, for instance, Mart and Peter, you have any inputs on the nature of the architecture?
It's agentic AI really that's going to be driving this. So, when the iPhone came out, there were 5 apps on the iPhone. There's now 2 million, and there's 3 million on the Google phone. What's going to happen, we think, is that you're going to see the appification, horrible word, appification of AI, where it becomes, in general use anywhere, and somebody's got to manage those apps everywhere, just like we did with the iPhone. The other thing is, you've got to remember, historically, when mobile phones started, if you remember, there was one mast that tried to broadcast as far as it possible. And then someone came up with a bright idea of distributing that and creating these cells. Well, it's not a stupid idea, So when you transfer from one cell to another, it comes with you. That's what we think is going to happen with computing.
Distributed AI.
Yeah,
Definitely. Yeah.
Mm-hmm. Well, then you will have to supply power.
and it needs
I'll
cables.
go for it. No, I agree with you. We can go to the next stuff. I fully follow your vision, for sure.
Yeah, and I want to open, since this is an energy, let's say, conference, related to conference, I wanted to ask some question. Everyone is seeking for different reasons, environmental or positive, let's say, environmentally friendly or sustainable, you name it. But of course, at the end of the day, there is always an economic component to that. Okay. Having said this, I personally thought, with my data center, let's say, design build background, that we would be by now, or these days, seeing more behind the meter, data centers across, the world. And this is still not happening in a large scale. Maybe you are starting to see some proof of concept here and there, but renewable energy is something extremely well rooted these days. And for instance, Spain, for instance, accounts for 70% of their, let's say, energy mix. It comes from renewable, or 75. So but still there are no behind-the-meter data centers. And this is kind of shocking. What do you think the future will be behind the meter? Do you think, well, the next future? And for instance, for smaller, let's say pods or data centers, how do you manage this in a metro area with limited, let's say, rooftop?
Yeah, well, there's a number of things there. I mean, we're in a sort of energy conference here, so there's a few things we need to realise. That a lot of people complain about the amount of electricity that data centres use. Well, it's not wasted. Every watt that goes into a data centre effectively comes out as heat. So the question is, what are we doing with that heat? It's the heat that's being wasted at the moment. There's not much you can do with gigawatts of heat if you're in the middle of the Nevada desert, except up into atmosphere. Whereas there is in metro areas, you can obviously reuse that heat. So all our designs enable us to reuse the heat and plug into district heating networks or swimming pools or whatever you want to do. But it's the reuse of that heat. So I think we should be focused on the potential for reusing that energy rather than focused on the number that people see, which is gigawatts of electricity being used, and water, by the way, as well. Everyone's focused on water. New data centers don't use much water at all now. So I think we're barking up the wrong tree sometimes.
Yeah,
Maybe I think what's interesting from a technology perspective, there are a few, like a really good example is, I now forget who it is, but I think it's Google contracting Form Energy for their first 100-hour battery. So there are technologies that are going to bring more ability to actually for data centers to be more flexible. There's another great startup, they were actually on stage with us last year here, Exowatt. They make a solar plus battery solution. So there are more and more solutions for a data center to go, fully behind the meter. Obviously gas turbines are one too, but I think that's one of the hottest commodity items you can currently find in the market. At the same time, there's many industries who've tried this, right? But coming from the utility industry, it's also many times been proven that the economies of scale that you gather by plugging into the grid are really hard to break. Yeah. And a good example, one of the hyperscalers we've been in discussions with, they've been pretty honest, they think it's a 2x or a 3x increase in cost still just powering your data center with gas turbines behind the meter versus connecting to the grid, even if a higher electricity price. And that just makes it really, I think there are solutions coming, but it will not beat what we have with just by connecting to the grid. That's simply the most cost-efficient way. The one thing that drives it now, I think, in the US at least, is speed. It was mentioned in the former panel, if anything is important now, it's speed to energization, and that's worth more than apparently worth more than a 2 or 3 times cost increase. And that's, I think, it's the race of the models, who's the first to develop the best and the best performing model. But so, I think there's a double-sided answer. On the one hand, the economies of scale of the grid are hard to beat, but if you want to get to the market fast, there are solutions that can get you there.
So you're pointing that probably the battery storage will become more relevant in the data center, let's say, infra.
Also adding flexibility to the grid, right? I think that's a big discussion in Europe, but also in the US, how can data centers become more of a player of adding flexibility into the energy system? Right now, they need too much reliability to actually provide that, but if you have a battery that you can use to actually power and move power back to the grid, that becomes an asset that can also provide flexibility to the market.
And here goes one question for Dell. Okay. Are you, let's say, starting to market some DC-powered, well, I guess, yes, of course, but, can you elaborate a bit on the DC? We are seeing more 800-volt DCs, coming from the Open Compute project, OCP, pushing this kind of new standard because different efficiencies, of course. What is Dell's, approach to this?
Yeah, first I just pick up on just something that the guys were saying, because that's a really interesting, very important part, and definitely that will fall into answering your question. I agree with what you were both saying. I think when we look at an ecosystem, there's the edge, there's the core, and then we heard this whole thing about the cloud. Well, the cloud is right across everything, right? But there's the edge, the core, and then there's public domains. And we really, really do need to analyze and understand where the data is, where the information is, what's driving the consumption. Now, here's the real interesting thing. And this is what I wanted to say. So we've talked about where we place the different types of current and future technologies. That could be, traditional silicon, could be quantum or hybrid quantum computing, could be 3D optical computing, right? And it could be neuromorphic architecture. And a lot of these are out there and in the and in play at the moment, to answer your point, right? So we're definitely and have been definitely very, very focused on quantum and hybrid, what we call HQCC, which is hybrid quantum classical computing. Clock speeds, energy consumptions, it's a completely different paradigm. As with 3D optical computing, like I mentioned earlier on, it handles the transfer of information through light diffraction and so on and so forth. This is not Star Wars. This is happening today. There are technologies and architectures that you can land into ecosystems and have them drive specific workloads. Now, this is the crux of what I wanted to get to. The specific workloads today versus where they're going to be in these timelines that you're talking about, 2030, 2040, are going to be significantly different, and B, in a significantly different place. They're going to be exactly where Peter told us they're going to be. And don't take my word for it. If you go and speak to McKesson, you go to speak to Gartner, you go to speak to IDC, they will tell you that all of the new workloads, all of the AI-related workloads are going to land out near where the event happens. They're going to happen at the edge. That's a statement of fact. So we've got to make sure that, and we haven't even talked about governance, compliance, controls, and policy in terms, so we've talked a lot about hyperscalers. Hyperscalers, they can't bring that. They have on-prem variants, but with them, they bring their own control plane. So localization of data and true sovereignty of data and ownership of information and patterns becomes a big problem for them. Whereas building this type of capability that's connected, edge connected directly to the core with that level of governance, compliance, and control and policy built in, allows us then to look at, okay, if 80% of the workloads are in the data center today, maybe there'll be 60 to 65, 70% of those workloads that are starting to move out from a percentile perspective to the edge. How do we power for that?
Well,
And how do we power for that? It's a big one. 400 gig of power we've got to find from somewhere.
Yeah.
Now, whichever side of the fence you set on the climate change discussion, there are some people that think it's fake news, believe it or not, but it's not. So, we're going to have, there is only a finite...
Earth is not flat then?
There's somebody, I don't know. But there is only obviously a finite supply of fossil fuel anyway. So whichever side of the fence you sit on, one day it's going to run out, and we're using more and more power. So we do have to find a way of, I think renewables will play a big part somehow, and whether it's wind or solar or nuclear.
And again, that's a conversation, though, Peter, around, well, where do we get this? So you come to my place, or you come to Ireland, you're not going to be very successful with solar, but you will with wind, right, if you harvest it. So it's understanding what kind of renewable energy you want to tap into and where it's best placed to be able to...
I think PPAs,
Yeah. But we have a big problem, right? When we do have a big problem whereby sustainability, which was the very, very top of every CEO's agenda this time 5-6 years ago, isn't anymore for obvious reasons that we all know.
Yeah.
I do think that's nomenclature, though. I think these are waves. Like now it's affordability, it's resilience. Yes, sadly, there's also more gas turbines in that sense being bought. But I think if I think about, in the end, a lot of the former technologies that really won when it came to the sustainability angle were also the ones that were economically viable, right? Mm-hmm. So I do think there's a hope, or I'm an optimist, so I hope that that's the case, and that also if another political swing will move back. Can I really quickly hit on what you said about 800 volts DC? Because I know we don't have a lot of time, but I think this is a fascinating discussion, right? We see NVIDIA, we see hyperscalers, we see neoclouds really driving towards an architecture that focuses on 800 volts DC. And that's necessary. We believe that's necessary too if you want to need more power in a confined space. Yep. What's really interesting is how the OEMs are responding to that. So we know that there's some high-efficiency bus bars in development. For us, it also means as a startup that we can capitalize on this, say, moving faster than an OEM. But we see there's a lot of, say, debate around when it's going to happen. But to be quite honest, like whether it's 2028, 2029, we are pretty certain that by then we will see the first DC-based architectures online.
Yeah, I think the summary is that we are moving into more efficient let's say, hybrid architectures, application-driven, okay, not so much technology-driven, but of course, application leads, let's say, systems architecture, and also what I believe is that also distributed computing at the edge will also probably, drive for other efficiencies, like for instance your power distribution systems, in the sense that probably you don't need tier 3 data centers anymore, since you will have redundancy built across, your network.
Well,
So,
yeah, but
so that will drive to efficiencies in any case, right?
you think about it, so where this is all going. You said agentic architectures. I agree with that, but it's kind of agentic architectures. Maybe, for example, blending with things like robots. So you think of robotics. You'll have your data center in a surgery, right, where a surgeon is conducting, an operation on a human. And you're not going to have to go back to your data center. Everything that you need from a power and from a computing perspective is going to be right by the surgeon's scalpel.
Yep.
So it's thinking differently around how we see AI today versus how we see AI moving forward, and then thinking differently around how we compute and power for that.
Okay, please, 30-second closing statement, Mart.
I don't think we've seen half of it. The world is going to change by the AI models, but also the way architectures looks like. So we'll have everything. We'll have SSDs, we'll have superconductors, we'll have new types of breakers, and that's all going to develop at a pace we've never seen before. Like, it's an extremely exciting time. I think
Thank you,
a good way to end.
Peter.
Yeah, we need to rebuild the internet. I think that's what we need to do right now. It wasn't built for what we're trying to do today. So there's a little job for somebody.
And Mark?
Yeah, well, we're going to have to augment it anyway, definitely. I don't know about rebuilding it. I agree. But, I think we're going to have to think about architecture very, very carefully. We're going to have to understand it better. And, I do agree, though. I think the world is changing very, very quickly. Most of us are adapting to that, but it is exciting.
No. Well, thank you very much. I don't know whether there are any questions, or maybe after the, after we wrap up, maybe you may jump in. Any question from the audience? Everyone? No? Okay. Then
Thank you, Henry.
We may close it.
Thanks,
Thanks very
Henry.
much. Thank you.
Thank you.
Well done, chaps. Sit down.